Let's continue with section 14.5, surface area. What is the idea here? So we had these surfaces. We talked about these, say, surfaces. And we talked about the volume bounded by these surfaces and other planes. Now, there is something else we can discuss, and that's the area of the surface itself, right? The area of this surface, so the area of this surface. So for example, do you know when we have a sphere with radius r, does anyone know what is the area of the sphere? Of the sphere with radius r? What is the area of the sphere with radius r? 4, well, we have different things. 4 pi r squared. 4 pi r squared. Does anyone know why that's the case? Does anyone know the proof? So why? The one good way, that is true. One good way is integral of volume. So you can say first, what is compute the volume of a sphere? You can compute the volume of a sphere the ways I just mentioned. And you would see that would be the volume of sphere. Now you can, it's a pretty interesting thing to think about. I don't want to spoil it for you, but you can convince yourself if you take derivative of volume of sphere, you would end up with the area of sphere. Right? If you take derivative with respect to r, from volume of the sphere, you get to area of the sphere. And it's really interesting to think why that's the case. Now, there is another way of understanding that, and that's this surface area, which I'm going to talk about now. So if I have a surface, suppose the surface is given with a function z equals to f of x and y. So for example, in our case, for the case of sphere, we know x squared plus y squared plus z squared equals r squared is the equation of the sphere with radius r. It means I should let f of x and y to be equal to z, right? Z here is equal to r squared minus x squared minus y squared. It's a square root, plus or minus. We can take plus. We can look at the northern hemisphere, compute its area and multiply it by 2, right? If I compute the area of the semi-sphere, if I multiply it by 2 at the end, I would get the area of the sphere itself. If I want to compute the area of any surface, here the sphere, but in general, f of x and y can be anything, the area would be equal to, look at this region here. Look at the red region. Well, when I'm writing with red, I don't think it would be necessary to write red, but anyway. Let's show this, let's note with this red region with r. I should take double integral over r. Exactly by over, I mean what we did before. You would see it in an example of this thing. Square root of 1 plus derivative of f, partial derivative of f with respect to x squared, plus partial derivative of f with respect to y squared, dx, dy. That would be the area of this surface. It's pretty interesting why that's the case. Why this is the case. I would just give you a hint, and the hint is cross product. So I'm not going to prove this formula, but I would just give you a hint. If you want to understand why the area of any surface is given with this equation, you should think about the cross product. Let's look at one example. Let's first look at this example we have here of this sphere. So z in the sphere, z is equal to r squared minus x squared minus y squared. So I should take double integral of this thing. Oh, sorry. I should take double integral of this thing. Square root of 1 plus. I should take partial derivative of this function with respect to x. So what is there? So I should let z to be equal to f of x and y. I should take derivative of this function with respect to x. What is derivative of this thing with respect to x? I should take derivative of what I have inside with respect to x. Would be minus 2x. And then I should divide it by 2 times this function. Similarly, I should take the partial derivative with respect to y. I would end up with minus y over r squared minus x squared minus y squared. I can cancel this 2 with this 2. Now I should square these things. I would get x squared over r squared minus x squared minus y squared plus y squared over r squared minus x squared minus y squared. So that's the formula for finding surface area over the region R. I would tell you what is this region R. Now, first of all, this thing here under the radical, if I simplify it a little bit, it would be equal to r squared. If I add all of these 3 things, it would be r squared over r squared minus x squared minus y squared dx dy. Now, what is this region R? Well, this means we should find the correct bounds for x and y. What are the bounds for x and y? Well, x squared plus y squared plus z squared equals r squared. Just ignore z. We get x squared plus y squared equals r squared. It means x is r squared minus y squared. It's the square root from plus minus. It means these are bounds for x. So minus square root of r squared minus y squared to r squared minus y squared. What are the bounds for y? Well, just ignore x. Y would be plus or minus r. These are the bounds for y. And then we should compute this integral. Again, this might be a little challenging. If you are persistent enough to compute this thing, what would be the value you would get? Can you guess what is the value you would end up with? Can anyone guess what is the final value of this integral? No, it would be actually 2 pi r squared. So not 4 pi r squared. Because it's just the upper semisphere. We're just looking at half of the sphere. So we should get that, and if you multiply that by 2, we should get the area of the sphere itself. That's how we compute the area of a surface. Let's look at one more example, an easier example maybe. An example of the question says, consider this surface z equals to 2 minus x minus y. Look at find the surface area of the portion of the plane z equals 2 minus x minus y. that lies above the circle x squared plus y squared less or equal than 1 in the first quadrant. Okay, does anyone want, oh, okay, you can. Okay, find the surface area of a portion of plane which lies above this circle. So what does it mean? Look at the three-dimensional space, okay? We have equation of a plane here. Z equal to minus x minus y is a plane, something like that. And then it gives us the equation of a circle. X squared plus y squared is equal 1 is this circle. Less or equal than 1 means inside the circle. Okay? It says look at the part of this plane which is above this circle, which is would be something like this, only in the first quadrant, means this part. I'm not sure if it's really visible, if you really can see what's going on here. It's a little tricky to imagine what's happening. So here in xy plane, we have the circle x squared plus y squared equals 1, right? This is a circle. We can look at x squared plus y squared less or equal than 1, which means inside the circle, right? Now it says consider only the first quadrant. The first quadrant means, well, let me draw it again. It means this part of the circle, only this part. This part of the disk. This is the first quadrant, okay? Now, if we look at this plane, maybe it's better for me to sketch the plane again. There is some part of this plane which is exactly above this 1/4 of the circle, this part of the plane. The idea is that to compute this area. Okay, I would do it. So the area is equal to integral of 1 plus partial derivative of f with respect to x squared plus partial derivative of f with respect to y squared dx dy over the region R. What is the region R? The region R here is this quarter of the disk we have here. This is R. This R should tell us what are the bounds for x and y. Okay. Okay, so z is equal to f of x and y. What is the partial derivative of f? We should do the computations first. What is the partial derivative of f with respect to x? Well, I should take derivative of this function with respect to x. It's -1. So partial derivative of f with respect to x squared is just 1. What is partial derivative of f with respect to y? Well, it's again -1. So partial derivative of f with respect to y squared is equal to 1. Okay, so I should compute the integral of double integral of 1 plus 1 plus 1 dx dy over this region. Okay, what are the bounds for x and y? So I have x squared plus y squared less or equal than 1. Here I have this region R. The point is that here, this is an interesting example. I really don't need to compute the bounds for x and y. Why? So let's see. Here I have this region R. This region R is this quarter of disk. I have this disk x squared plus y squared less or equal than 1. I'm looking at it only in the first quadrant. This is R. I should take double integral times the square root of 3 dx dy. Okay. Square root of 3 is a constant, comes out of integral. Integral of 1 dx dy over r. Does anyone know what is this integral? What is integral of 1 over any region? What is integral of 1 over any region? It's simply area of that region. Yes. What is the area of R? Well, it's 1/4 of a circle. What is the area of a circle? Pi r squared. Here is 1 squared. So the final answer would be pi square root of 3 over 4. So that's the surface of that part of the plane above this region. That's how we compute the surface area. Sometimes we might need to do change of variable. We might need to go to polar coordinates, but that's the idea. There is a rule called Simpson's rule. As an approximation. Oh, how did I get the square root of 3? Well, let's go back. The surface area is the integral of this thing. The square root of 1 plus partial derivative of f with respect to x squared plus partial derivative of f with respect to y squared, right? Here, partial derivative of f with respect to x is -1. So it would be 1 plus -1 squared plus partial derivative of f with respect to y is -1. So it would be -1 squared. So it comes from here. It would be 1 square root of 1 plus 1 plus 1. Where does this formula come itself? Why this thing is the surface area of a surface? I didn't prove that. I just mentioned whenever we have a surface represented by a function f, the area of that surface is equal to this integral. Square root of 1 plus partial derivative of f with respect to x squared plus partial derivative of f with respect to y squared. Okay, is there any other question? Okay, so you can compute the surface area for a sphere yourself. It's not really hard to do. For other surfaces like ellipsoid and paraboloid and etc., it's not really something easy to do anymore. It's kind of complicated. So, or paraboloid, or etc. You can't compute it explicitly, but you can find approximations. A lot of times you can approximate an integral. It's something I wouldn't go into, but in the book, there is something mentioned, Simpson's rule. It's quite an interesting approach to approximate an integral when we can't compute the integral directly. And I guess a lot of computer programs, they use this method to compute the integral. Okay. So let's have a short break now. I think it's good time for a break. Let's have a short break. After the break, I would talk more about triple integral. We mostly worked with double integrals. Now we should talk a little bit about triple integrals. That's what we would do after the break. Any questions? Okay, let's come back at 11:45.